Hey, Stephen.
Hello, Dr. Sean.
Hey, how's it going?
Good, you?
Good, good. Let me grab some water. In fact. I've been looking for this.
Oh my god, really?
Yeah.
You just told this during the convention.
Oh, I forgot about that. I've been like doing calculations like on Microsoft Calculator. with this thing.
Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today?
Good, how are you?
Good, good. Yeah, end of the week. This is my last lecture of the week, so it's exciting. Okay, so the plan for today is we're going to finish up our last two examples. So I believe we had two more examples that I wanted to go through from the MATLAB review. Okay, so I'm going to switch over from my PC soon and go over that. And then after that, we're going to start our review of fluids. Okay. And so, we're at the end of week 2 and we're still doing review stuff, but that's just kind of the nature of this class. Is there's a lot of stuff to review before we get started. So, and so we're gonna spend some time, hopefully review some things that look familiar to you from 333, and then that's going to set us up for actually doing some new stuff with cardiovascular. Okay. So before I get started, are there any questions I can answer about the homework or about what we covered last time?
Can you go over the last example we went over, please?
Yeah. So I'll kind of redo that one, and then I'll go over the next two examples, and then we'll go from there. Yeah. Okay. So let's go ahead and get started. Okay. So let's go back to this example right here. Okay, so we're back on our MATLAB review, and so here I have the slides on the left, and then our code on the right. Okay, and so the example that we left off with was using an if statement in a for loop. Okay, and so if statements and for loops were kind of the last two things that we went over as coding techniques, and they can be combined. Okay, and so in this particular example right here, we're using an if statement to basically check which entry in the vector that we're looking at. Okay, because remember the for loop, what it's going to do is that it's going to count up from 1 up until 20, and it's going to iterate basically 20 different times. And then what we're going to be doing is we're going to use the loop index here to refer to specific entries in this vector. Okay, and so if you look at this example here, we start out with an empty vector, so we can say that we have we created this vector called even vector, and it's a vector of all zeros, and it has 20 elements. Okay, and then what we're going to do is we're going to loop over all 20 elements and assign a value to it depending on what index we're at. Okay. And so that's the for loop here. So the for loop is mostly just responsible for making sure that we go and visit every single entry in this vector, okay, all 20 of them. And so what the if statement here is going to do is that it's going to allow our code to do something different depending on the value of the index, okay? And so this code that I have right here, so I have if mod vector index comma 2 equals 0. And so what this line of code essentially is going to do is it's going to check to see if our vector index is an even number, okay? remember, this vector index is going to be counting up between 1 and 20. And so half the time it's going to be an odd number, and then the other half the time is going to be an even number. And so on the times where it lands on an even number, we want to do something special, okay? And so the way to kind of read this code is to say, we're running this mod function, okay? And so remember what the mod function does. So the mod function finds you the remainder after division, okay? So if you kind of think back to, when you first learned division, before you learned about fractions and decimals, whenever you perform division with whole numbers, a lot of the times you would perform the division and you would have a remainder after that, okay? So as an example, let's do 9 divided by 2, right? And so normally 9 divided by 2, for a college engineering student would be 4.5, right? You would say 4.5 and you wouldn't think again about it, right? But then if you ask your cousin who just learned about division, I don't even know how old they learn division nowadays, maybe in 5th grade, right? What they'll say is that 9 divided by 2 is 4, remainder 1, right? And so because 2 goes into 9 4 times, and then, but after you do that, then there's still a remainder of 1 after that, okay? And so that's what the mod function will do, is it'll find that remainder for you, okay? And that's really useful for a lot of cases, specifically for, determining whether a number is even or odd. Because if a number is even, when we divide it by 2, we should get no remainder, right? And so all the even numbers you divide by 2, you should get remainder 0. But for an odd number, if you take the remainder after dividing by 2, you're going to get 1, right? It doesn't matter what the odd number is. It could be 9, which is what we just said, or it could be 1,337. And so you divide that by 2, and you're still going to get remainder 1. Okay. And so what this if statement here is that it's going to check what that remainder is. Okay. And so if the remainder after dividing by 2 is equal to 0, then we can enter into this if statement here and apply something specific. Okay. And in this case, we just want to do something simple here, where we set the value of that entry equal to whatever that index is. Okay. And so if you look at kind of this, let me kind of zoom in because it's like impossible to read. Okay? And so if you kind of look at this entry here, the output here, you can see for all the odd numbered entries, we still have 0 because we skipped over them because they failed the if statement. But for all the even number entries, you can see we've set the value of that equal to whatever that index is. We have 2, 4, 6, 8, 10, 12, and so on and so forth. Okay. And so this was an example here of how we can use an if statement in a for loop, specifically using an if statement combined together with the loop index to do something a little bit clever. Okay. Okay. So any questions on this example here? Okay. All right. So now let's jump into the last 2 examples. So these 2 examples here are a little bit of a step up, and so they're a little bit more complicated, just to kind of give you some additional looks, right? Because the thing with programming is that if you ask someone to define what an if statement does or define what a for loop does, I think most people would be able to tell you. The difficulty isn't defining what that is. The difficulty is actually using it in practice. And the only way you kind of get better at that is practicing it yourself, or you can see how other people do it too. So I wanted to make sure I give you guys at least these 2 examples so that you have some more things to look at. All right, so let's read the statement for this problem. So in this example, we're going to start with an empty 5 by 5 matrix, and then we're going to fill each row of the matrix according to the following criteria. Okay, and so for the first row in the matrix, what we're going to do is we're going to start with 2. Okay, and then each entry in the column after that is going to be counting up by 2. Right, and so the first row should read 2, 4, 6, 8, 10. Okay, and then in the second row of that matrix, we're going to start with 3, okay? And then each entry in that one should count up by 3, okay? And so the second row should read 3, 6, 9, 12, 15, right? And then so on and so forth. So each time we move to a different row, we're not only increasing our starting value by 1, but we're also increasing the amount that we're counting up by 1, okay? And then on the right here, you can see kind of the implementation of this. Okay. And so the first thing we see is that we have to create our empty matrix. And so this was kind of the first line in the problem statement. And so we're saying that we're starting with an empty 5 by 5. And so that's exactly what this zeros command is going to do, okay? And then from there, you know, we need to visit every single entry in the matrix, okay? And so if you think back, if you look back to our example on nested for loops, we know that nested for loops are a great way to visit, you know, every single entry in a matrix, okay? And so in this case, we have a 5 by 5. And so what we're going to do is we're going to have a nested for loop where each of the loops goes from 1 to 5, okay? And so with this, you know, we can, with this structure here, we'll be able to visit every single entry. And then if you name your variables like this, then it's pretty clear, you know, what these loop indices are going to be used for. So one of the loop indices are going to is going to refer to the rows, and so the rows are going to count up from 1 to 5, and then the other loop index, the inner one, is going to be the column index, and so that's again going to go from 1 to 5. And so if you kind of follow the logic of this loop, you know, remember the outer loop. In order for the outer loop to increment and go on to its next iteration, the inner loop has to finish its job, right? And so the way to kind of visit each entry is that you start here, right, in the top left. And so this is the first row in the first column. And then we follow the inner loop. So the inner loop is going to go column 1, column 2, column 3, column 4, column 5. Okay. And then after we finish that, then the outer loop increments by 1. So outer loop, we go back to, we now are in number 2. And then the inner loop, once again, iterates from column 1, column 2, column 3, column 4, column 5, okay? And then so on and so forth. Okay, and so that's the loop structure. And so now let's actually start to assign values, okay? Right. Okay, so the first thing that we need to do is we need to assign kind of the first entry in the row, right? And we know that the first entry in the row, you know, we start with 2, and then each row after that we go up by 1. Okay, and so I've defined this extra variable right here called count. And so count, you can kind of think of it as our starting value for that row, right? And so the value for count here will be the row index plus 1, right? And so the row index refers to which row in the matrix we're in, and we add plus 1 to kind of satisfy our conditions, right? And so the plus 1 is just there to make sure that for the first row we started 2, for the second row we started 3, for the third row we started 4, and so on and so forth. Okay. Okay. And so with that, you know, we can go ahead and assign the value to the matrix. Okay. And so just like we did up here, we're going to, you know, say that the row index and column index entry of this matrix is going to be equal to count. Okay. All right. And then as the inner loop iterates, we need to also increase count by 1, or not by 1, by, you know, the amount that's specified for that row. And so within the inner loop, we're going to have this line right here where we have count is equal to count plus row index plus 1. Okay. Where again, we see, you know, row index plus 1 to kind of make sure that we're counting up by the correct amount for that row. Okay. And then I've used the update notation here to make sure that, you know, we're updating the value of count on each iteration, right? And remember, the way you read these update notations is that you say that the new value of count is going to be equal to the old value of count plus these new values right here. Okay. All right. And so with that, you know, that should be able to give you this this output over here. Okay. All right. Any questions on this example? This example here?
Wait, just for some, I guess review. So, so on the first one, on the first for loop, it will go it will first choose 1, and then it'll go enter on the second for loop, and it will go 5 times.
Yes.
Right.
Yep. Mm-hmm.
And then once it's done with that, it's gonna go against the first for loop and go choose number 2, and then
Yep.
keep. Okay.
Yep. Yeah. So think of it like a clock. Remember, so the inner loop is kind of like the minutes hand, and then the outer loop is like the hours hand. So every time the hours hand goes up by 1, then the inner loop already made kind of a full rotation.
Thank you.
Yep. Mm-hmm. Okay, so let's go on to the second example. Okay. Okay, and so in this example here, we're going to start out with an empty vector, and so we're going to start with a vector with 25 entries, and then what we're going to do is we're going to loop over each of the entries and modify each value according to the following criteria. Okay, and so if the index is an odd number, then we're going to change the value to 1. Then we're going to check if the entry is a multiple of 4. Then if that's the case, we're going to change the value of the entry to 4. And then in all other cases, we're going to change the entry to 24. Okay. So you can almost think of this as kind of like a step up of kind of the very first example we did today, where we had the if statement in the for loop. Okay. And if you can look at the solution right here, you can see we have an if statement inside our for loop. But this time it's an if, else if, and else statement. Okay. All right, so let's go through this implementation, right? And so the first thing we see here is that we have to create our empty vector, right? And so we see, we use the zeros command once again to create a vector that's going to be empty, right? And so this is a vector that has 25 entries to it. And then since we have 25 entries here, we're going to loop over all of them. So our loop index needs to go from 1 to 25, okay? All right, and so from here, we're going to enter our if statements. And then, we're going to check all the different cases here, right? So let's check the first case first. The first thing we're going to check to see is if the index is an odd number, right? And so to check if it's an odd number, we're once again going to use the mod command, right? And so we're going to divide these two numbers, which is vector index, and we're going to divide it by 2, right? But this time we're looking for odd numbers. And so, for odd numbers, when you divide by 2, you end up with a 1 as a remainder, okay? And so if that's satisfied, then we enter the body of that if statement, and we say that example vector 2 at vector index is equal to 1. Okay, and so that's basically setting the value of that vector to be 1. Okay. All right, so that's the first condition. And so the second condition here is to check to see if the index is a multiple of 4. Okay. And so to check to see if it's a multiple of 4, we can once again use the mod command. And so we can say mod vector index and 4, right? And if the index is a multiple of 4, then if you divide by 4, then you should get no remainder, right? Because that's the definition of being a multiple, right? So if you take 4, you take 8, you can take 12, 16, 20, 24. All of those numbers are multiples of 4. So then if you divide by 4, you get a nice round number, and you shouldn't get any remainders. Okay, and then just like the problem statement says here, is that if that's the case, then we're going to set that vector entry equal to 4. Okay, all right, and then the last thing that we have here is that in all other cases. So remember, whenever we have something where we want to satisfy for all the other cases, for that case we use an else. Okay, so else is going to be, for all the other cases. Remember, else is if the first two conditions failed, then do this. Okay, and so in all other cases, we're going to set the value of the entry equal to 24, which is what we have right here. Okay, and then if you do all that, then the output looks something like this. Okay, and so you can see for all of the odd numbers, so 1, 3, 5, 7, 9, 11, 13, 15, all that stuff, you can see we have a 1 in that slot, right? So just like what the code states. Right? Next, we're going to check all the multiples of 4. So we're going to check entry 4, 8, 12, 16, 20, and 24. And you can see that all of these have a value of 4 in their spot. Okay, and then all the other entries that don't satisfy either of these criteria, so it's the index is not an odd number, and it's not a multiple of 4, then for all of those cases we have 24, and you can see them all right there. Okay. Okay. So any questions on this example here? Okay. Right. So that's 2 more examples for you guys. So one example, another example with a nested for loop, and then an example with else if else statement. Okay. All right. So the last thing
Professor?
Oh yeah. Mm-hmm.
Actually, could we go back to the nested for loop?
Yeah. Mm-hmm.
It's because it still trips me up doing the inner count equals count plus row index plus 1, like visualizing it. Could we do like an example where you like plug in numbers so to see an action?
Yeah. Let's do that. Okay, so let's do kind of this first row right here. Okay, so we'll evaluate this code kind of line by line. Okay, so the first thing we do is we establish kind of this empty 5 by 5. So we can say that this is kind of empty. Actually, let me pull up Excel. That might be the easiest thing. I hate this new thing with Microsoft Excel. Just give me a blank document. I don't know when you would not want to do a blank document. Okay. So we have our empty 5 by 5, and so we have 5 5, like that. Okay. And we're going to start with the first row right here. Okay. And so let's go through this for loop, right? So we say for row index is equal to 1 to 5. Okay. And the first thing we are going to do is we're going to set count is equal to row index plus 1. Okay. All right, so let's compute what that is for the first iteration, right? And so for the first iteration of this loop, row index is going to be 1, right? Okay, because that's just the first iteration. And so if row index is 1, then when we compute count, it's going to be row index plus 1, okay? And so if row index is 1, then this is going to be 1 plus 1, which is equal to 2, right? And so count is going to be 2. Right? Okay. And so now that we have count, let's go ahead and just kind of store that to the side because we're going to use it in a little bit. Okay. And so from here, we're going to enter the inner loop. Okay. And so the inner loop here, we're going to start looping from 1 to 5. And so for the first iteration of the inner loop, we have column index is equal to 1, okay? And so what we're going to do is we're going to set a value for this example matrix. And so the column or the row that we're going to specify here is row index. And so since row index is equal to 1, we're going to have a 1 right there. And then we're going to, our next coordinate is going to be the column index, which is going to be 1. Okay. And so we're going to set the top left entry, so the 1, 1, which is going to be right here. Okay. And this is going to be whatever is in count. Okay. And so if we look at line 137, we see that count is 2. And so we can say that, you know, example matrix 1, 1 is equal to 2. And so let's go ahead and put that here. Okay. Okay.
Wait, how does MATLAB know that that's going to be what count is?
Because we define count up here, right? It's because remember the MATLAB reads your code kind of top to bottom. So if it's reading this line first, then count is already defined to be having a value of 2. Yeah. Okay. Does that make sense?
No, I'm still confused.
Yeah. Okay. So the so whenever you have a MATLAB code like this, it always reads it kind of from top to bottom. So any line that you have above is going to be evaluated before every line below, right? And so if we compare lines 129 and 131, in 131 we're asking MATLAB to recall the value of count, right? And so at that point, you know, MATLAB goes in and says, you know, do we have a variable named count already? So it's kind of looking in its memory banks, and so you can see right here that count was already defined 2 lines above that, right? And so because of that, MATLAB's like, oh, you know, count was already defined just 2 lines prior. So let me find the value of count, which in this case was 2.
Yeah. I guess what I'm asking is that on the first for loop, you have the row index equals 1 to 5, right?
Yep. Mm-hmm.
And that means that the first number is 1, right?
Yes. Mm-hmm.
And then, but how does MATLAB know that count will be 2 after you do the addition? Does that make sense? What I'm asking?
Right. Yes. So
I know count is 2 because you add 1 plus 1 and you get that 1 from the 1 to 5.
Yep.
How does MATLAB know that count will go at the first row, first column?
Right. So count is kind of separate from that. So count is just a scalar variable that we're kind of keeping off to the side, and so we're kind of updating that on our own. And so MATLAB actually doesn't know that, you know, this is actually associated with this matrix at all. So think of it as kind of like a variable that we're kind of updating just on our own. And so in this case, you know, we're using count and we're correlating it with the row index right here. But remember, row index, the loop index itself is also a variable, right? And in this case, it's just a variable that just counts up from 1 to 2 to 3 to 4 to 5. But on each specific iteration of that loop, you know, the loop index is just going to have a singular value. And so for this one, for the first iteration, row index is going to be stuck at a value of 1 until we come back up to the outer loop, and then row index is going to update its value to 2. Does that kind of help a little bit?
Yeah, yeah, I think it helps.
Okay.
I think so. Pretty much, it turns 2 after it reaches the second for loop, right?
Exactly.
Where you define example matrix 1, row index, column index equals count.
Exactly, right. So yeah, by the next time, it comes back up to the, so basically, once you reach this part of the code right here, it's going to come back up to line 128 right here, and then evaluate this again. And so anytime you have a loop, the way you kind of read this, you're going to evaluate everything here, and then you're going to come back up to the top of the loop. But then when you come back to the top, your loop variable here is going to go to its next value. So we're going to go through everything here, and then when it comes back up to the top, row index is going to go from 1 to 2. Yeah.
Okay, it makes sense now.
Yep. Great. Okay. And so, in the inner loop right here, we're actually going to update the value of count one more time. Okay. Because in our output here, we want to have basically 2, 4, 6, 8, 10, right? And so each time we move to a column, we move to the next column, we want to update count to be kind of the next value. Okay. And so the way that we do that is we have this line of code right here, which is count is equal to count plus row index plus 1. Okay. And so the way to evaluate that code is we can say that count, the new value of count, is going to be the old value of count. And so in this case, the old value of count was 2. Okay. To that, we're going to add the row index. And so for this iteration of the loop, since we haven't come back to the top yet, row index is still going to be 1. Okay. And then to that, we're going to add 1 again. Okay. And so we're going to have 2 plus 1 plus 1. And so now count is going to be equal to 4. Okay. All right. And so now that count is 4, we reach the end of this inner loop. And so now we're going to come back up to the top of just the inner loop because, this is the one that we're stuck at, right? Except now that we've come back to the top of the inner loop, column index is now going to be 2 because we've reached the second iteration of that inner loop. Okay. And so now we're going to specify the value of example matrix 1 at row index and column index, but now column index is 2. So we're going to change this guy to 2 right here. And then count now is going to be 4. Okay. So let's go ahead and pop that into our matrix here. And so that's going to be 4. Okay. And then now we're going to continue on with from here. Okay. And so after count is equal to 4, we're once again going to add row index and 1. And so the new value of count is going to be the old value, which is 4. And we're going to do plus 1 plus 1. And so the new value of this is going to be 6. Okay. And then we assign that entry into this one. So this will be 6. This is going to be 8, and then 10. And so we're basically going to keep doing this until the inner loop finishes all 5 iterations. And then we're going to reach the end right here. And then now we're going to come back up to the top of this loop. Okay. And then by the time we come back up to the top right here, row index's value is going to be 2. Okay. And so now our starting value of count is going to be row index plus 1. So it's going to be 2 plus 1. And now this is going to be 3. Okay. And so now, we're just going to repeat kind of the same thing. So on the first iteration of the inner loop, we're going to have row index, comma, column index. So now that row index is 2, we're going to start at entry 2, comma 1. Okay. And then now we're going to use our starting value of count, which is 3. Okay. So now that places a 3 right there. Right. And then we're going to update count according to row index plus 1. So now our row index is 2. So we're going to do that. Okay. And then so now we have this. Okay. So we have 3 plus 2 plus 1. And so this is going to be 6. Okay. And then 9, and then 12, and then 15. Okay. And then we kind of just continue on with this logic up until, up until we reach the end of that matrix. Okay. Right.
Okay, thank you, Professor. That really helped me understand it.
Great. All right. Yeah, that one is it's a modern logic, but I think if you kind of break it down and kind of know, and you kind of keep track of all the different variables in there, then it kind of helps it make sense. Okay.
Yeah, true.
Okay, so let's go over the last thing I want to cover in MATLAB, which is plotting. Okay, and so plotting is actually, I think one of the nicest features within MATLAB because it allows you to kind of very quickly kind of make a plot of your or visual of your data. Okay, and visuals of data is actually very underrated because it kind of helps you see things that is really hard to see in numbers. Okay, and so to create a plot, it's very simple. So the first thing you have to do is call this command right here called figure, and so you're going to do figure parentheses 1. Okay, so that means we're going to run the first figure, and then we're going to use the command called plot, And then from here, you have to feed it two different vectors. Okay? And so the first vector right here will hold the values for your x-axis. Okay? And then the second vector there will hold the values for your y-axis. Okay? And so in this example here, I'm just plotting a simple quadratic function. And so we're going to have x is equal to just the lin space from 0 to 5 with 100 entries. And then y is just going to be x squared. Okay. And so if you run this code, what you have is just your simple quadratic function that looks like that. Okay. All right. And so the code I deleted just now is for the last lecture that I did this, people asked about putting multiple plots onto the same figure. And so you can do that using the hold on command. Okay. And so let's say that we have a second function here, which is a cubic function. So let's say that we have z is equal to x cubed. Okay. And so if we want to put this onto the same plot as we have here, we can use the MATLAB command called hold on. And so that literally tells MATLAB, said, hold on, don't move on to the next figure yet. I'm still putting stuff here, right? And then after you put hold on, you can just simply call the plot function again. Okay. And so in this case, let's say that we want to plot our z function with a cubic one. Okay. And then when we're done with our holding, we can just say hold off. Okay. And then you can see here we've added a second line to our graph here. Okay. And so the plot that we have in red, there's our cubic function. And so you can see that since it's a cubic, it goes up a lot faster than the quadratic function. Okay. And you can keep doing this too. So let's say that we want to plot a fourth order function now, right? So let's do x comma x raised to the fourth. Okay. You can see here we've added another line. Okay. All right. So one subtle thing that I want to point out here is that you'll notice that I've also added this period here, right? And so I didn't simply just say that y is equal to x squared. I had to do y is equal to x dot squared. Okay. And so what that dot basically says is that, we want to perform these operations kind of element by element. Okay. Because, when MATLAB sees x, it sees x here is a vector, right? And so when you say, y is equal to x squared, what it's going to do is that it's actually going to try to perform vector-vector multiplication, right? So it's going to take one vector, another vector, and then try to multiply it. And it'll be a mess, okay? And so we don't want that. We don't want the vectors themselves to be multiplied, but we want the entries in the vector to be squared, right? And so to kind of do this kind of element by element operations, we have to add this period right here, okay? And so that's just kind of a primer on those periods. So you'll see those kind of quite a bit to kind of to tell MATLAB to not do vector-vector operations. Okay. Okay. So any questions on plotting? Okay. All right. So that's the MATLAB review. So hopefully that was helpful to everyone. And so, I'm actually, developing a lot of the lectures or the content for the class, as we speak. So I'm almost up to everything for the first midterm, and we'll see MATLAB to kind of varying capacity. So it's kind of good to have these on hand. And even besides this class, MATLAB is just kind of a good general skill to have that you can use professionally, right? Because just like we said last time, MATLAB is relatively really cheap. And there's a lot that you can do with MATLAB that's really useful for a lot of things, right? And so kind of having just kind of basic skills in MATLAB is just, really, really good to have. Okay. And so, oh, sorry. The chat just doesn't work for me again. It doesn't notify me when you guys are saying stuff in the chat. Sorry about that. I totally missed all this stuff in the chat. Okay. So I think hopefully everything was satisfied in the chat. But were there any other questions from the chat? It seemed like things were satisfied, but if not, let me know. Okay. All right. So now let's go ahead and start the next set of lecture notes which we have, which is going to be our review of fluids. Okay. And so today, we're just going to be doing just pretty gentle review stuff. So we're going to go over things like fluid properties. So we'll go over things like velocity, density, viscosity, and flow rate. And then we'll start to look at, how do we actually, solve for fluid mechanical quantities using the Navier-Stokes equations. Okay, so we'll see Navier-Stokes again, and then we'll see, how we actually use that for blood flow. Okay. Okay. So let's go ahead and get started. So here is going to be our review of fluids. Okay. Okay. All right. And so fluids is going to form the basis for a lot of what we're going to do in this class, because we're talking about blood flow, right? And so blood, if you've if you've ever seen it or touched it, blood, it behaves like a fluid, right? So I said behaves like a fluid because, kind of like what we talked about before, blood is technically a suspension of, of a bunch of cells in a plasma, right? But for most of our cases where we're going to focus on just the large arteries, blood is basically the same as fluid. So we're going to do that, okay? And so, because of that, our knowledge of fluid mechanics as engineers is going to serve us really well when we're analyzing blood flow, okay? And so in particular, I want to focus on just kind of the simplest representation of blood flow in an artery, okay? And so the way that you can do that is you can just simply have a cylinder, okay? And so the cylinder here is our blood vessel, right? So all your blood vessels are cylindrical in shape to a degree, right? And then blood's going to flow in the middle of it, okay? And so to drive flow in a cylinder like this, usually what you're going to have is you're going to have a pressure difference, right? And so on one end of the cylinder, you're going to have a pressure P1, and on the other side, you're going to have P2, right? Okay. And in order to drive flow forward, P1 has to be greater than P2, okay? Okay. And so we're also going to have a radius of the cylinder. So let's say that, our radius is given by big R, okay? And then, along the cylinder, we're going to have our velocity, okay? And so our velocity here is going to be given by U, which is going to be a function of R, right? And so just to kind of draw our coordinate axes here, we're going to find the R direction to be, going from the center of the cylinder out. That's going to be our radial direction. And then the Z direction here is going to be the direction down the barrel or down the length of the cylinder. And we call that our axial dimension, okay? Okay. And so, there's going to be a lot of factors in here that's going to affect our velocity or affect our blood flow, okay? And so let's go over some of the physical properties of fluids, that you should remember fluid mechanics. We'll define what they are and kind of discuss, how that's going to be important for blood flow. Okay. Oops. Okay. And so before that, let's go ahead and give a formal definition for a fluid, right? And so this is kind of the first definition that you'll see in your fluids class. And so a fluid is simply just any substance that continuously deforms under an applied shear stress. Okay. And so the key words that I want you guys to focus on in this definition is continuously deforms, okay? And so if you apply a force to a fluid, it's not just going to displace, right? And so that's different from solids, because if you take like, this mouse right here and I kind of squeezed it, right? And so in that case, I'm applying a force, but because this mouse is a solid, it's just going to kind of squeeze in a little bit, it's going to deform, but after a certain point, it's going to stop deforming, right? But for a fluid, if you apply a force to a fluid, it's going to continuously and keep deforming, right? And so this, this continuous deformation here, we often call this flow. And that's kind of the biggest kind of defining characteristic of a fluid there, which is, if you apply a force to a fluid, it's just going to keep flowing, right? So if you think of like the fluid that comes out of your faucet, or, take this water, you pour it upside down, right? So that fluid is just going to keep flowing, okay? And so the way that we kind of describe motion, or we describe the movement of fluid, is through its velocity field. Okay. And so the velocity field here is basically a description of how fast the fluid is moving at different locations in space. Okay. Okay. Any questions on this so far? Okay. All right. And so let's look at kind of a basic example for a Cartesian system. Okay. And so when I say Cartesian system, what I mean is that the coordinate system is defined by x and y. Okay. And then the velocity field, or the velocity distribution, would be, how the fluid is kind of moving in this field. Okay. So let's say that we have a velocity field that looks like this. Okay. And so this velocity field would be u of x and y. Okay. And so what this u of x and y here tells us is the velocity of the fluid as a function of space. Okay. And by space, all I mean is basically it's x and y coordinates. Okay. And so for engineering purposes, a lot of times we're interested in solving for this velocity field, right? Because if we have the velocity field, you can actually compute almost everything else that you would be interested in for fluid. So the velocity field is very valuable. But the difficulty is that, solving for this velocity field can be really difficult because it usually involves solving the Navier-Stokes equations, which, most sane people don't like to do for fun. So, when you're solving for the velocity field, that's kind of the holy grail, but, a lot of times you can't get there because it's really hard unless you have a really powerful computer, which is what we'll have. Okay. Okay. And so that's the velocity. So velocity fields are very important because that's how we define, or that's how we describe the motion. Okay. But there's also a lot of physical properties within the fluid that affect its motion. Okay. And so we'll go over two here, two, I think, of the most important ones. And so the first one we'll go over is the density. Okay. And so the density formally is a ratio of the mass of the substance over a unit volume. Okay. And so usually density, we give it the symbol rho. And so it looks like a little p right here, okay? But it's curved. That tells you it's not p, okay? And so it's going to be the ratio of mass of substance over volume. And so the density is an implicit property, right? And so what that means is that, you know, it's a property that doesn't depend on the amount of substance that you have, right? And so whether you have like a small cup of water right here, or you have a gallon of water, or you have, you know, a big tub of water, right? All of those waters should have the same density, you know, given that they're at the same temperature. But and so, you know, whether you have a small amount or a large amount, the density is going to be the same. Okay. And so this is really important because for fluids, you know, fluids are usually almost always constantly in motion, right? And so it's hard to kind of describe its mass in kind of the same way as we describe mass for solids too, right? And so, because like if we have like a solid object like this mouse, we can easily just weigh this and say, you know, this mouse is this much. So we can compute its weight or its mass by that. But for fluids, since it's always in a constant state of motion, right? How do we say, you know, what's the mass of the blood that's flowing through your arm, right? Because it's flowing, right? And so a lot of times, you know, we're going to use density to describe its mass because it's something that's implicit. Okay. All right. And so the density is really important for us because, you know, just like, you know, as you can imagine, for solids, you know, the mass of the object kind of determines its inertia. You know, the more dense a fluid is, that's also going to give it more inertia as well. Okay. And so inertia, if you kind of recall, is how we describe, you know, how well that object resists change in motion, right? And so something with a high inertia will, you know, will want to keep its state of motion, right? And so the way I like to think about it is inertia kind of describes how lazy that object is, right? Because if you have something that's really massive and it's sitting still, it's going to take a lot of work to like push it, you know, and to try to give it some momentum because it has a large amount of inertia, right? And then once an object with a lot of inertia gets going, it's hard to stop it because it wants to kind of retain its state of motion, right? And so for fluids, it's the same way. So if you have a fluid that's really dense, it's going to take a lot of work to get it moving at first. And then once you get it moving, it's hard to stop it because it has a lot of inertia. Okay. Okay. Any questions on this? Okay. All right. So that's density. And so density is going to be important for us to remember. Next, let's go over viscosity. And so viscosity describes, you know, how sticky or how thick a fluid feels. Okay? Okay, because if you think of some fluids that have a high viscosity, so something like honey or something like molasses, right? If you go and you stick your hand into a jar of honey, it's going to feel kind of really gross to take your hand out because all the honey is going to cling to your hand, right? And so that's kind of like the qualitative description of viscosity, but kind of a more precise description is, you know, or is it describes a fluid's resistance to flow. Okay. Okay. And I'm going to qualify this this description a little bit more, just to kind of differentiate it from density. Is that more importantly, it helps it resist shear stresses. Okay. 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 And so kind of the fundamental formula here for viscosity that I want you to know is this formula right here. Okay. Right. And so on here, on this left-hand side, we have tau. And so tau here is going to be a shear stress. Okay. This du dy right here, this is going to be the velocity gradient. Okay. And then this mu right here. And so I know with my handwriting, it looks like a capital M, but it's actually a mu, right? And so think of it as like a U with like an extra kind of face mask. That's what I think of it as, okay? And so this right here is our viscosity. Okay. And so basically what the viscosity does is it defines this relationship in between the shear stress and the velocity gradient, okay? And so let me draw a picture for you to kind of describe, you know, what this is, okay? Right. And so let's say that we have a rectangle here, and this rectangle here is some parcel of fluid, okay? Right. And so this parcel of fluid is just kind of sitting there, kind of minding its own business. But then all of a sudden, we're going to expose this parcel of fluid to some shear stresses. Okay. Okay. And so let's say that we expose this this fluid to, you know, a shear stress. So we have one on top that's going to be pushing the top of the fluid to the right, and we have another shear stress on the bottom that's going to push the fluid to the left. Okay. And so what's going to happen to this fluid is that it's going to start to deform, right? Okay. And so our fluid might look something like this after a bit of time, okay? Oops. Okay. And so here, you know, let's say that a couple seconds have passed, and after those couple of seconds, you know, we have this the fluid parcel was kind of displaced this amount. So the bottom of the fluid has gone to the left, and the top of the fluid parcel has gone to the right. Okay. And so we can define this angle right here, which is the angle from which, you know, the that's formed as a result of the forcing. Okay. And this angle right here represents the strain on the fluid element. And so it's basically kind of a measure of how much this fluid element is deforming, okay? Okay. And so if we take this strain and then we take the time derivative of this will give us the strain rate, okay? And the strain rate is going to be, you know, is going to form back into this formula up here. So before I do that, are there any questions on this? So let's define the strain rate. Right. And so the strain rate is going to be nothing more than just the time derivative of theta, right? Okay. And so it's the rate at which this this fluid element is kind of deforming as a result of the shearing forces. Okay. The top right of my iPad is not cooperating. Okay. Okay. So that's the strain rate. And so another way that we can express the strain rate is actually in terms of the velocity gradient. Okay. And so if you actually go through the derivation, what you'll find is that d theta dt, okay, is actually equal to du dy. Okay, and so du dy right here is an expression for how the velocity is changing in space. Okay. Yeah, I'm still using my old iPad. It's my new one is still broken, but it's broken a different way now. So I really need to take it to a new. I really need to take it to a repair shop. Yeah, the pen's not that great too, which I'm sad because I paid like $60 for this, but you know, it is what it is. Okay. Okay. And so the velocity gradient here describes how our velocity is changing in space. Okay. Okay. Yeah. Maybe I should just get a new thing, but it's also expensive, man. Okay. So it turns out, the strain rate is actually the same as this velocity gradient right here. Okay. And so if we go back to our formula here, which describes our viscous stresses. Okay. Okay. Then we have this formula, right? And so now we kind of have a new interpretation of the viscosity here, which shows that it kind of defines the relationship between the shear stress and the strain rate. Okay. All right. And so this is really key because, strain rate on the right here, which is du dy, that can be almost like a surrogate for, how much the fluid is deforming, right? And so what this expression basically tells you is that for fluids that are highly viscous, right? So for fluids that have a high level of viscosity, in order to really get it moving, in order to really, have a high velocity gradient, you need to apply a lot of shear stress, right? And so that kind of goes back to our definition of viscosity from the previous page, which says that the viscosity is kind of a measure of how well a fluid will resist flow. Okay, and so kind of the mathematical or kind of the calculus kind of reasoning behind that is shown here, right? And so fluids with high viscosity basically require a lot of shear stress or a lot of force in order for them to flow really well, in other words, in order for them to have a very high strain rate. Okay. Any questions on this? Okay. All right. And so all that is, you would see kind of all that in just like a fluids class. But I want to make kind of one more distinction here, which is a point that we're going to come back to a lot in this class, right? And so let me kind of draw a typical blood vessel here, or at least a cross section. Okay. So here you might have your endothelial wall. Okay. Okay. And so let's say that we have blood that's flowing in here, right? And so let's say that we have a velocity field that looks like this. Okay. So next week, what we'll do is we'll solve the Navier-Stokes equation so that we can actually find out what this velocity looks like. Let's just assume that it's parabolic for now. Okay. What we can do is from this velocity field. So let's say that we have u z of r. Okay. Okay. From the velocity field, we can compute the viscous shear stress. Okay. Okay. And the way that we compute it is we basically just use the same formula that we had previously. Okay, so we have tau is equal to mu du. In this case, we have uz. Okay. And instead of y, we're going to take the derivative with respect to r. Okay. So r is our radial direction. Okay. Okay. And so this this right here, this viscous shear stress, this is kind of a measure of the friction that the blood, the friction force that's being imparted by the blood. Okay. Okay. So this is, this is something that we can actually compute at the sides of our vessel wall, right? And so let's say that we compute the viscous shear stress at the walls, okay? Okay. And so in other words, if we compute the amount of viscous shear stress that the fluid is imparting at the walls, this is almost like the friction force that the blood imparts onto the wall. Okay. Okay. And so it's almost kind of the same thing where, like, if you take two solid surfaces and kind of rub them against each other, there's going to be a friction force that you feel, right? Because you have friction of two solid surfaces, right? And so a fluid is exactly the same thing. So if you have fluid that's flowing past a surface, right, then there's going to be a friction because the fluid is going to try to drag that surface kind of along with it, right? And so blood is kind of the same thing. So every time blood flows in a vessel, there's going to be some friction drag force that's going to be, is going to be imparted from the blood onto the vessel wall. Okay. And so this viscous shear stress is going to be very important for us later. So we're going to give it a name. And so this viscous shear force is going to be called the wall shear stress. Okay. Or WSS. Okay. Right. And so you'll hear this term come up quite a bit in this class. And wall shear stress is nothing more than just the viscous friction force that the blood imparts onto the vessel wall. Okay. And it's basically a direct result of the fact that blood is a viscous fluid, and it's going to have some viscous stresses with it. Okay. Right. So this is really important because remember, your blood vessel walls are not just rubber tubes, right? So they're actually lined with living cells. And those living cells can actually feel this viscous force, believe it or not, right? So as the blood kind of moves past these cells actually feel it, right? And so, your cells are all living creatures, so they have ways that they can sense forces on them. And so they can actually sense the wall shear stress of the blood that's imparting onto it, right? And they actually use that wall shear stress to trigger a lot of biological and chemical processes, right? And so depending on, what the wall shear stress that the cells experience, they might trigger some things, say like, hey, maybe we should make the vessel bigger, or hey, maybe we should make the vessel smaller, or maybe we should release this protein, or maybe we should release this enzyme into the blood, right? And so this shear stress right here, which is, very much a fluid mechanics thing, right? We're going to compute it using Navier-Stokes, which is, an engineering equation. That's actually going to be the trigger for, a lot of biological processes too, right? And actually, this wall shear stress actually modulates a lot of the activity in your cardiovascular system. So this is going to be a principal, quantity that we're going to be interested in this class, because it triggers so many things inside your cardiovascular system. Okay, any questions on this? Okay. All right. And so one more thing I want to talk about, which is technically not a property. Oh, question. So wall shear stress is the shear stress caused by blood onto the vessel wall, making it pretty much a blood force applied to blood vessels. Yep, exactly. Yeah. And so we'll talk about this in a couple of weeks, but the blood actually imparts basically two kinds of forces onto your blood vessel walls. And so there's the viscous wall shear stress that we just talked about. But also the fact that blood is pressurized, because it's basically a pressurized fluid that's going throughout your system. There's also going to be a normal force onto the vessel walls that's due to pressure. But it also imparts like a shear stress, which is in the direction of the blood vessel, and that comes as a direct result of viscosity. Yeah. Mm-hmm. Okay. So one other thing I want to mention, which in my fluids class, I do a bad job of kind of talking about this, is I want to mention the flow rate. Okay. And so flow rate is another term, you'll see that's used to describe fluid motion, okay? But flow rate here is going to be different than velocity, right? And so velocity, remember, has units of length over time, right? So velocity, usually you give it units such like meters per second or miles per hour, right? So it's any kind of length over time. Flow rate is different than velocity. So flow rate describes how much volume is moving as a function of time, okay? Okay. And so the typical units for flow rate will be just any kind of measure over time, any kind of volume over time. So it could be like meters cubed per second, right? Or more commonly for blood flow, it might be milliliters per second, okay? Because a meter cubed is really big. So you don't have that much blood in your body unless you're, Timmy the Giant or something, right? And so usually for a normal sized human, we measure volume of blood in terms of milliliters, okay? And so flow rate, whenever you see something in milliliters per second, that describes flow rate, okay? And so the common symbol that I'll give for flow rate is Q, okay? And the way that you compute it is you take the velocity of the blood and you multiply it by area, okay? And so let's say that, we have blood that's flowing into a vessel like this, right? And this cross section right here has an area A. Okay. And you have blood that's flowing through here. So let's say that, we've computed just the mean velocity across that face, okay? And so if you take the product of the velocity times the area, what you're going to get is the flow rate Q, okay? And if you work out the units for this, you'll see that it's a volume over time, because you have length over time from the velocity, and then you have length squared from the area. And so you take their product, you get length cubed over time, which is volume over time, okay? Okay. Any questions on flow rate? Okay. Right. And so with flow rate, we can start to express some of the conservation laws within fluids. Okay, because when you're talking about fluid motion, the way that we often describe it is we use conservation of mass and we use conservation of momentum. Okay, and so the one that we'll use mostly in this class is Navier-Stokes. But let me give you just kind of an intuitive feel for conservation of mass, just because this example is kind of quick. And I think it's really useful, okay? And so let's say that, we have a vessel with just one inlet and one outlet, okay? But let's say that the vessel gets smaller, Okay. 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 So this often happens in the cardiovascular system because usually, you know, as you measure the blood vessels coming from your heart and all the way downstream, the blood vessels tend to get tinier and tinier. So, you know, what we call that is that the blood vessel diameter tends to taper as you go through the cardiovascular system. Okay. All right. And so coming in here, we have a flow rate. Okay. So we have a certain volume per time. Right. And then the question here is, you know, what's the flow rate that comes out of here? Okay. Okay. And so it turns out, you know, when you have a single inlet, single outlet system like this, what you have to apply here is conservation of mass. And so conservation of mass basically states that, you know, the mass that enters this tube here can't be created. New mass can't be created and it can't be destroyed. Okay. And since, you know, we're going to assume that this tube is relatively rigid, you know, basically what conservation of mass says that everything that comes in has to come out. Okay. And so a certain volume of blood will come in a second, and then that same volume of fluid has to come out because it's, you know, there's just nowhere else for it to go. Okay. And so by conservation of mass here, what we have is that the flow rate in has to equal the flow rate out. Okay. Because otherwise, you know, something went wrong, and you know there's a bug in the simulation that's running our world, right? Because you know we can't have any mass accumulate and we can't have any mass be destroyed. So basically, whatever comes into a system has to come out. Okay. And so let's do kind of let's do another example with another common case you'll see in the cardiovascular system, which is, you know, when a vessel kind of branches off into two. Okay. Okay. And so let's say that we have flow coming in here, and then we have flow coming out of these branches. Okay. Right. We can once again apply conservation of mass. And what conservation of mass basically will tell us is that all of the outflows have to equal the inflow, right? So whatever comes in, it has to come out, right? So in this case, we have Q in, right? But we have two outlets here. And so Q in is going to have to equal Q2 plus Q3. Okay. So that's why, you know, flow rate is often used to describe blood flow, just because it's, you know, it has this kind of very nice conservation of mass quality right here. Okay. All right, any questions on this? Okay. All right, so we have about a little bit less than 5 minutes left, and so we won't be able to do too much more, but I do want to kind of jog your memory a little bit about what I think are the most important equations in fluid mechanics, which are the Navier-Stokes equations. And so I used to tell my fluids class that I love the Navier-Stokes equation so much that I named my Wi-Fi after Navier-Stokes. And so you walk into my apartment and, you know, you see your phone, you said you're connected to Navier-Stokes 5G. I'm like, damn right you are. But I moved to a new place and I haven't changed the name of my Wi-Fi yet. But all my devices are connected to the generic Spectrum Wi-Fi name, so I'm too lazy to change it now. And so, you know, the Navier-Stokes Wi-Fi has kind of died with my old place. Okay. And so the Navier-Stokes equations, you know, they look really intimidating, and they are because they are intimidating. But you know, at their core, all they really represent is just the conservation of mass and momentum for a fluid. Okay. Right. And the way it expresses this conservation of mass and momentum is with partial differential equations. Okay. All right, so let me just write it down really quick, and then we'll pick this up next time. Okay. Actually, let me just write down the conservation of mass one. Right? All right, so the Navier-Stokes equation for conservation of mass is given by the following. Okay. And so this is the conservation of mass. Okay. Another name for this conservation of mass equation is called the continuity equation. Okay. All right, and so what it basically says is that if you take u, where u is the velocity in the x direction, you take its derivative with respect to x, you add that to partial v partial y, where v is the velocity in the y direction, and then you add that to partial w partial z, where w is the velocity in the z direction. You add all these guys up, you should get 0. Okay. And so this is kind of the differential equation form for conservation of mass. Okay. All right. Any final questions on this? Okay. All right. So that's all we got time for today. And so on Tuesday, we're going to pick this up again. We're going to pick up with Navier-Stokes, and we'll kind of review how we actually solve these problems. And then after that, we'll actually apply it to one of the more important laws in blood flow, which is called Murray's Law. Okay. All right, so thank you guys for tuning in as usual. So hope everyone has a good weekend. Remember, your first homework is due on Tuesday, so make sure you do that. And if you have any questions on that, let me know. And besides that, have a good weekend, and I'll see you next week.
Thank you.
Thanks, guys. Yeah, so if you're in 417, then the MATLAB questions are exactly the same. Yeah. So if you do one, you can double dip and you can use the same thing for both. Yeah.
Professor, quick question on can you show me how to from start to like how to create a code on MATLAB?
Oh, just to create a code on MATLAB? Yeah,
just like a simple one, just because I haven't really used it, so I'm trying to figure it out. Like from start, do you go to a new script first?
Yeah. Let me show you how to do that. Yeah, Josh, I sent you an email about your question for 3C. So go ahead and check that one out first. And if that doesn't make sense, you can you can ask again. Yeah. Okay, so let's go back here. Okay. All right. And so when you first open MATLAB, you'll come to this screen right here, which is this is called the console, or at least I call it the console, right? And so to actually start writing a code, you would have to go to new script right here, and this opens up another window here where you can start typing out some code. Right? And so let's see, let's do one of the examples. Let's just write this code right here. So in a new script, what you can do is that let's say that we want to write loop vector is equal to the zeros 1, 5, and we do 4, index is equal to 1 to 5, end, oops, and then we'll do loop vector at index is equal to 2 times index. Okay. And so that's all you have to do. So you just have to make a new script and just start writing code, right? And then from here you can save it. And so I'll just call it Untitled for now, right? But you can obviously give it a nicer name and save it in a better place. And then from here, you can just hit the run button right here, right? And so the keyboard shortcut for run is F5, or you can just click the green button. So actually, I usually click the green button right here. So let me clear everything. Yeah. And so you run this code, and you can see here we have 2 variables here. So we have one variable for the loop index, which is 5. And then we have our loop vector, which is what we assign in the script. Yeah.
Oh, okay. I was having difficulty seeing the output. Like,
okay. Yeah. So the output isn't back in the console. So you have to I like to kind of keep it kind of split screen like this, so I can run the code and I can see the results in the console kind of right away. Yeah.
Okay. You double clicked on the that matrix the matrix right there that you made.
Yeah. Mm-hmm. Yeah. When you double click on it, then you can see the value of what's inside right there. Yeah.
So in the editor, that's where you actually write your script.
Yeah.
And then, so what exactly is this workspace thing?
Workspace. So this workspace kind of it enlists all the variables that you've created in your code. And so basically any variable that you create, you can see it here and you can check its value, right? And so let's create a new variable. And so let's say that this is going to be a linspace from 0 to 10 with 101 spots, okay? And so as soon as we create this new variable and we hit run, you can see that new variable will show up here on the workspace. Yeah. And so you can double click it and you can check all of its values here.
Okay, and I'm not getting the icon of, well, the run. I'm not getting that one. I just I don't know how it says run on time. Is that this? Does it same thing? No.
It should be actually. I've actually never tried this. Let me try it. It should be the same actually. Oh. So
That's not something I'm getting, but
you can just hit F5 if you want to run it. So if you have the editor as your main window, just hit F5 on your keyboard and it should run. It should just simply run the code. Because if you hit run in time, I think it'll pop up with this profiler, which is kind of annoying. So so I think a lot of times you don't want to deal with that. So you can just hit F5. So let me try that right now. Yeah. So F5 should be able to just run your code.
I don't know what I did. I hit F5 and my it closed out.
Oh really? Oh shoot.
I'm a PC. Is that the same? Is that on PC or Mac?
I'm on PC right now. Yeah.
Oh, okay. I don't know what I did, but I closed it out. All right, I'll give it a shot.